Using classical physics, John William Strutt, also known as Lord Rayleigh, and Sir James Hopwood Jeans derived an equation that explained blackbody radiation, but only at very low frequencies. Classical physics refers to the principles of physics that include Newton's laws of motion and Maxwell's theory of electromagnetism. The failure of classical physics to explain blackbody radiation and other phenomena led to the development of quantum mechanics, which is considered as one of the two pillars of modern physics, the other being Einstein's theory of relativity. In the figure shown here, the black curve is the Rayleigh-Jeans prediction at 5000 Kelvin. Note that the horizontal axis is wavelength. Since wavelength and frequency are inversely proportional, the left side corresponds to high frequency and the right side corresponds to low frequency. Very low frequencies correspond to very long wavelengths. In other words, there is a good agreement between the experimental spectrum and the Rayleigh-Jeans prediction on this part of the chart. However, we can see that at shorter wavelengths, the agreement gets worse. Although both curves increase as the wavelengths get shorter, the experimental curve, shown here in blue, eventually reaches a peak, then the intensity of the emission goes back down at even shorter wavelengths. But the Rayleigh-Jeans curve predicts that the emissions just keep getting even more intense at very short wavelengths. Not only does the Rayleigh-Jeans equation fail, but it fails miserably since it predicts that everything will emit an infinitely intense radiation. Since ultraviolet radiation is associated with wavelengths shorter than those of visible radiation, this incorrect prediction of the Rayleigh-Jeans equation is known as the ultraviolet catastrophe. The Rayleigh-Jeans law is mathematically given by this equation, which expresses the spectral energy density per unit frequency, typically represented by the lowercase Greek letter rho, as a function of frequency nu and temperature T. The spectral energy density refers to the total energy of electromagnetic radiation in the cavity divided by the volume of the cavity. It has units of joules per meter cubed. Since rho is energy density per unit frequency, it has units of joule per meter cubed per hertz. Or, since hertz is per second, the unit of rho can also be written as joule per meter cubed times second. The spectral energy density can be shown to be directly proportional to the intensity of the light, so we can think of a plot of rho versus frequency as essentially a plot of intensity versus frequency. At a given constant temperature, all the quantities on the right-hand side of the equation are constants except for the frequency nu. C is the speed of light, 2.998 times 10 to the 8th meters per second. And K sub B is Boltzmann's constant, which is equal to 1.38 times 10 to the negative 23 joules per Kelvin. It is clear from this equation how the Rayleigh-Jeans law predicts the so-called ultraviolet catastrophe. The equation says that rho is directly proportional to the square of the frequency. Please pay particular attention to this part of the equation. K sub B times T is the average energy of the charged particles oscillating at frequency nu in the cavity. If one were to assume that there is no restriction in the amount of energy that an oscillator can gain or lose, it turns out that fixing this is the key to making theory agree with the experimental spectrum. The frequency of radiation emitted by a black body corresponds to the frequency of a charged particle oscillating at that same frequency. When an oscillator at a given frequency gains energy, it ends up being able to stretch out farther at the same frequency. Conversely, losing energy means that the oscillator will not be able to stretch out as far. Planck was able to fit the experimental blackbody spectrum by making a radical assumption. He assumed that the energy of an oscillator is quantized. By quantized, we mean that there are restrictions. Specifically, he assumed that the allowed energies are multiples of h nu, where h is a constant. This means an oscillator with frequency nu can only have energies of h nu, 2h nu, 3h nu, and so on. For example, if an oscillator happens to have an energy of 2h nu, it cannot gain an energy of 0.1 h nu, because that would raise its energy to 2.1 h nu, and 2.1 h nu is not allowed. If an oscillator happens to have an energy of 3h nu, it can lose an energy of 1h nu, because that would take its energy down to 2h nu, and 2h nu is allowed. A consequence of this assumption is that higher frequency oscillators are less likely to gain energy compared to low energy oscillators, and this causes emission intensity to drop back down to zero for very high frequencies, which would be consistent with the experimental observation. With Planck's assumption, this becomes the expression for spectral energy density per unit frequency. The difference between this and the Rayleigh-Jeans equation is the expression for the average energy of particles oscillating at frequency nu. It is now equal to h nu divided by e to the power x minus 1 instead of k sub b times t. Here, x is the ratio of h nu to kb times t. Planck didn't actually believe in quantization and intended to eventually see if the equation would fit the experimental spectrum as the value of h approaches zero. It turns out h has to be a very small number, but not zero. H is now called Planck's constant, and its modern value is 6.626 times 10 to the negative 34 joule second.